So I start with this because as we get into other systems, you need to know how to interpret what's going on with them, right? When you run a hydraulic system, you want to be able to know what the pressure is or what the fluid quantity in the reservoir is. When you run the electrical system, you want to know what the voltage and the frequency and what buses are powered and everything. And so we'll look at how we can see that using the indication systems on the aircraft. Part of this discussion also includes the design of these indication systems. And the reason I discuss it, though most of you probably aren't going to be designing these, some of you may go into the aircraft development area. It's not just limited to engineers that are doing that, but there are technicians involved, people that have more of a maintenance background involved in that. But where it's important is the theory of operation for how these things are supposed to work plays a big part in troubleshooting because they don't always work exactly like what you would imagine they do. And so if I've seen instances where either flight crews didn't understand how an indication system worked, or even worse, maintenance didn't understand how an indication system was supposed to work. And it was, flight crews would write something up that was operating as intended, but maybe not how they expected. Or maintenance would be troubleshooting something that was operating how it was intended, but maybe not as expected. And so if you're troubleshooting something that's not actually broken, it's a big waste of time and resources and money. And so you have to understand that theory of operation and what's supposed to be happening to be able to effectively troubleshoot a system. And ultimately, at the end of the day, that's kind of the goal, right? You're getting your technician, you're getting your A&P, and you need to work on the aircraft, you need to repair the aircraft, you need to keep the aircraft serviceable and airworthy, and part of that is troubleshooting and making sure the systems are operating correctly. So looking at flight deck configurations, kind of the two you'll see out there nowadays, and in the first one I would say even less so than what we had before, is a 3-crew. We start with a 3-crew aircraft. And in a 3-crew aircraft, this is our 727. We have a captain, sits in the left seat. A first officer sits in the right seat. Those are the two individuals primarily responsible for flying and navigating the aircraft, as well as performing the communication functions using the radios. And then you have a flight engineer. And the flight engineer panel is typically located just behind the captain and first officer, and they are primarily responsible for system operation and monitoring. Newer aircraft, and mostly anything you're going to probably come across, unless you work on some older stuff, is going to be a 2-crew aircraft, and that is the captain in the left seat and the first officer in the right, with the elimination of the flight engineer. And we'll look at why that is, but now the captain and first officer, they are, in addition to flying the aircraft and navigating and communicating, they also are going to be operating the systems and monitoring them. But they have help that a lot of that has been automated now. And so you don't need that third person to perform that function of constant monitoring and system operation. There are jump seats in the aircraft. When we've been in the 727, how many seats are in that flight deck? Tell me. So we have a captain, a first officer, a flight engineer. Yeah, there's 5 seats up there. So those 2 additional seats that don't have any panels, they have a kind of a circuit breaker panel around them. They're on the left side. Those are what are called jump seats. Those are for a observer. In the case of like a crew member needs to have what's called a check ride. They get regular checkouts by a more senior flight a more senior pilot or by an FAA examiner. Okay, so every airplane, transport aircraft, at minimum has to have 1 jump seat because there's a requirement that it has that seat so that an FAA or company examiner can ride along in a certified seat. You can't just like shove an extra person in the cockpit and be like, okay, kind of stand there for the flight and hope you don't hit any turbulence, right? So they have to have at least 1. Many of them have 2. Larger aircraft tend to have 2 or even 3. But those do not count as flight crew. They are purely there as observers. The other thing they're often used for is for crew relocation. So say you need to get a pilot, say you have an extra pilot in Chicago and you need to get a pilot over to Denver, they'll jump, they'll ride in the jump seat rather than taking up a passenger seat. Frankly, in most aircraft, the jump seats, larger aircraft, the jump seats are more comfortable than riding in the cabin. Unless you can get first class, where you can actually have like a lay flat bed and everything. But there were, back in the day, 4-crew aircraft as well. These were phased out in the 1950s to 1970s. And in that case, you did have, your fourth was, you had a pilot or a captain and a first officer that primarily were dealing with flying the aircraft. And then you had the flight engineer with the systems. That fourth crew member would do things like navigation and communication. Okay, so they were operating radios and communication. They were using paper, charts, big paper charts, and having to plot stuff out, having to even take like fixes using old school navigation equipment and that kind of thing. So that was the first eliminated. Then the flight engineer was eliminated. Now we're down to 2 crew. And I would be surprised if in your lifetime we don't go to a single physical crew member. The flight unions really are fighting, the pilot unions are fighting this. The airlines are pushing for it, with automation, having the ability to have a single crew member in the aircraft. Most of the time it's flown remotely, but you have that one person there in case of an emergency situation. Even today, most of the flying done by these aircraft is on autopilot with a navigation system essentially running the show. The crews earn their money when things don't work like they're supposed to. Okay. Most of them do hand fly. A lot of them hand fly for takeoff and approach and landing, mainly in a lot of cases to keep proficient. But some of your larger aircraft, newest aircraft that are what's called Cat 3C qualified, the aircraft can basically do everything from takeoff through landing and rollout without human input, or with minimal human input. So here's just some examples. Here's our Boeing 727 on the left. Captain, first officer, flight engineer, you're familiar with that. A DC-10 on the right looks very similar. Captain, first officer, flight engineer here on kind of behind on the right. And then here's the 2 crew, kind of some of your earlier 2 crew. Airbus A320 on the left and a Boeing 767 on the right. You can see they're starting to get, here you have mainly analog instrumentation. Here you're starting to get some digital displays, but there's still a lot of analog, right? There's still a lot of not digital displays going on here. One thing I do want to point out, Airbus tends to use a side stick, or they use a side stick in their aircraft rather than a yoke in between the knees. Side sticks off to the side. Boeing and Embraer and Bombardier, they all use a standard yoke between the knees in front of you. Embraer 170 on the left, you can see the displays have gotten even bigger, take up more of the real estate on the, especially on the main instrument panel. 787 from Boeing on the right also has that. This also has, anyone know what this little thing is hanging down here, top left corner? What? Who said HUD? What's HUD stand for? Heads up display. That plate swings down in front of the pilot, and there's probably one on the co-pilot side as well. It's a customer option, how many you have. And it projects essentially this display down here up right in front of the crew. So it overlays a digital runway or a digital flight path in front of the pilots. So I don't know, the Embraer 170s might have it as an option. The CRJs did have it as an option. 700s and 900s, they had HUD systems. So. A lot of new cars. My wife's car has it. She doesn't like it. It's off most of the time. So what drove our transition from 3 to 2? Technology was what allowed it to happen. We used technology to essentially engineer out complexity in the aircraft. We've used technology to take over those monitoring functions, right? Things are now monitored by computers. And if there's an abnormal situation, that's when the flight crew is notified. If you think about the 727 panel, you're looking at that what they call second officer, the flight engineer, would have to basically kind of throughout the flight be scanning that panel and looking for a hydraulic pressure that doesn't look right. looking for a light to come on, looking for a gauge to show something that's abnormal. Now, if you get a low hydraulic pressure, a message pops up, a noise, you get a ding or a horn, and you're able to pull it up on those flat panel displays that are right in front of you. Okay. Technology is what allowed this to happen, but regulations originally stipulated that you had 3 crew members. So regulation had to change. So once the manufacturers were able to show that the plane could be operated safely by 2 people and that they had the information they needed, then the regulations adapted and changed to allow for that 2 crew flight deck. There was kind of an odd transition period. If you look at the 7, let's go back to this, 767. It doesn't really show it, but right here to the right, behind the first officer, there's this big empty panel. What's the big empty panel? Behind the first officer. The what? The what? It would have been a flight engineer spot if they needed a flight engineer. Now it's mainly a maintenance. There's some maintenance stuff on there. That's about it. And then it serves as a jump seat. It's got a little work table there. It's basically kind of what's in the 727, but without all the gauges and instruments on it. Besides some, like I said, some maintenance panels, circuit breaker panels, but it's still got a little work table there and stuff like that. The 757 and 767 both have it. They were developed during the 757, 767. Those are Boeing's first new from the factory certified 2 crew aircraft in this complexity level. The 737 was 2 crew, but it was smaller and didn't have to have that 3rd crew member initially. Okay, so regulation allowed it. And why the airlines pushed for this? The biggest reason was cost savings. Okay, and when I say cost savings, you've got salaries of pilots. Pilots are expensive. They really are. Space, you can move that wall forward a little bit. You get a little more space in the cabin. That's extra seats for passengers. Weight, that big panel is pretty heavy. So we get rid of that, right? Weight results in drag, and drag results in fuel use. So you can get the weight down. You have to train these people. The pilots have training and that kind of thing. Now you only have to train 2 people instead of 3, et cetera. There's other things that played into it as well. But the big thing, cost, you can save cost, okay? So when these are designed, and some things we need to keep in mind as we work on these, is that the flight deck is designed using ergonomics. So ergonomics is essentially the study of how your body operates in a given space. What is your posture sitting in the chair? How much twisting and bending do you have? Think of like someone operating a cash register at a checkout, right? They're grabbing the items here, they're scanning them, and they're moving them over here. That twisting, right? That falls into ergonomics. And in a flight deck, though, the pilots are sitting. That's a big thing. Some of these pilots might be sitting for hours and hours at a time on long international flights. You have to be able to get in and out of the flight deck without having to do gymnastics, right? So ergonomics plays into that. And to kind of design the cockpit, they used anthropometry, which is looking at measurements of humans. Early aircraft were based on the average human, the average pilot. What do you think the average pilot was in earlier aircraft? Who was the average pilot when aircraft first came out? What? Men? What else? Malnourished? Probably not malnourished. Okay, it was typically male. Does race play a role in the size of a person? Don't even dare shake your head. You can't deny it. Different races have different physical builds. I'm not saying I'm not being racist, I'm saying it's a fact. I've worked with a lot of people that have ancestry from the Pacific Islands. People from the Pacific Islands tend to have a bigger, stockier build. They're Not as nice, but they are stockier built. Okay, they're not. Some of them are really tall too. Most, some Dutch tend to be taller on average, right? The average Dutch male is taller. Someone has Dutch ancestry. So, originally the aircraft were designed around male, Caucasian, 20 to 30-year-old, right? Has done physical activity. What am I describing right now? Military, men out of the military. Typically around World War II, right? So that's what early planes were designed for. And what we found as we've gotten a more diverse crew is that some of these planes don't fit people really well. And so they've done a better job of designing these. Now, why I bring this up is because you as a mechanic are going to be working on this stuff. And there are times where you can make decisions on whether to release an aircraft for service with something inoperational. Not everything on the aircraft has to work 100% of the time. Some of these aircraft have upwards of 1 million parts on them. Sometimes they're going to operate with things broken. What if a seat height adjustment is broken? Does it make the aircraft unflyable? If the seat height is stuck at the lowest level, do you think it makes it unflyable for me? Probably not. Would it make the airplane unflyable for you? Probably so. You wouldn't be able to see, and I'm pointing to Adora, not nearly as tall as I am, right? You would have trouble seeing over the windshield. You might have trouble reaching that overhead panel. So we have to keep that in mind. Yeah, the regulations allow us to defer maintenance on a seat height adjustment, but a pilot may decide that, hey, you know what, I can't take this airplane because I don't fit anymore. And so you can look at the different things that have to be taken into consideration when these are done and when they're engineered, and especially if you get into aircraft design or aircraft modification, you have to take into account this kind of stuff. Okay, how many of you want to work in fuel tanks? Okay, guess who didn't have to work in fuel tanks very often? Me. My shoulders don't fit through the fuel panels very easily. Guess who got stuck working in fuel tanks a lot? Yep, I see a few people pointing to themselves. They tend to be smaller build, right? Shorter, more compact, small shoulders, right? Guess who didn't have to crawl under the lab floor very often because he couldn't fit between the seat frames? Guess who got stuck going under the lab floor? Guess who got a neck cramp every time he was under a wing taking panels off? Guess who could comfortably take panels off, right? So it applies to maintenance too. If I was going to go under and do a ton of panels on the bottom of the plane, I was probably going to put it up on jacks. It doesn't have to be done, but it's going to make me be able to do it a lot faster and a lot easier and a lot more comfortably. Okay? So, those kind of things you can take into consideration as you're working around the aircraft. So just some examples of this. Design, one of the big design key elements is eye position, as I talked about with the seat height adjustment. Can anyone see anything here that you can use to find eye position? Anyone know what's going on here? So what do I got to see out of this flight deck right now? I'm being able to see out the window, right? There's a runway up ahead. Okay, what else? But at the same time, so I got to be able to see that, but at the same time, what else do I have to be able to see? The ground, okay. Huh? Who said what? So if I'm sitting too high, I might have trouble seeing this top row of instruments, such as like my main engine instruments right here. So I got to be high enough to see out the window, but not so high that my view of the instrument panel is blocked. Or low enough to see the whole instrument panel, but not so low that I can't see properly out the window. Here's how we know. The 3 little balls. You'll see these on aircraft. It's not a great blown up picture, but if I was in the pilot seat, I would see this ball. I know my eye's in the right position when it blocks this one behind it. If I'm in the co-pilot seat, I'm looking this way. I'm in the right, my head's in the correct position when this ball blocks this one right here. Okay? Simple little thing like that. People see that, they're like, oh, one of the balls is missing. I don't even know what that's for. a couple of years, like a year, 18 months before I knew what the heck that thing was. I'm like, I don't know what this thing is. It's just in the front. And then someone's like, yeah, you use that to like line up so you can see. And once I started adjusting my seat so I could do it, I'm like, wow, I can actually see outside when I taxi. I thought I had my seat too low a lot of times before I realized what the three little balls. It's kind of like the three shells. Does anyone get the three shell reference? Nobody? No one's got the three shell? I'm getting old. It's a movie. It's an old movie. It's not an old movie, but well, okay. Flight deck design philosophy. So when we figure out where the controls are, or more importantly, when you get into an airplane and you're going to operate it, especially if you're operating it for the first time, you're going to have to find the controls. And so the typical kind of control layout should have some kind of logic to it. And some of those logical things are based off of oftentimes frequency of use. But is it your frequency of use? Whose frequency of use is a cockpit flight deck designed around? The operator. So the pilot. What are the pilots most interested in knowing? Okay, besides how much money they're going to make. Which way the aircraft's pointing. So if we go back and look at one of these cockpits, what's right in front of the pilot? Flight instruments, right? And then you can see engine instruments are pretty close. And then this we'll get to in a minute is a warning panel, right? Do you see any system controls on this? No, the pilots kind of set the systems and they go with it. You, as a maintainer, are probably going to be working with systems a lot more often. So where are the systems located on a two-crew cockpit? Where are they in the 747 sim we play with? Look up. Okay, most of your system stuff that you'll need to find will be on top. And that's pretty standardized, whether you're in a Boeing or whether you're in an Airbus or whether you're in a CRJ or whether you're in an ERJ. Systems controls are above. Flight instruments and engine instruments are right in front of you. Communications is down the middle. Okay, communication navigation is usually right down the middle, as well as your engine controls, your throttles, right? Steering tiller is off kind of to the side because the only time you use that's for taxiing around on the ground. Okay. So that's that standardization. Things tend to be in similar areas. Okay. Tactile. What's tactile mean? Feel. What's feel in our cockpit, in our flight deck? What would we feel? I'm going to go back to my flight deck here. That's not a great one. I don't have a good picture there. What kind of things might we be feeling for in the flight deck? There we go. There's a cockpit picture. Maybe we can pick out some stuff here. What are we going to feel for? Which is distance. Okay. What's this right here? Linear handle. What shape is that knob right there? Circular, like the shape of a wheel. Look at your knobs on landing gear handles. They are shaped like a wheel. Okay. What about this? Anyone know what this little handle is right here? Flaps. What shape is it? It looks like a little bitty flap. Okay. Throttles are almost always round like that. They're typically rounded. It's comfortable to put your hand on, but it also is kind of a standard design, so you know that's what the throttles feel like. So you don't necessarily have to reach down and grab them. Throttles are typically laid out in the same arrangement as the engines. Number one throttles on the left engine, right? It wouldn't make sense to be swapping those around. It has happened, by the way. A connector's gotten swapped and wrong sides control, yeah. Doesn't happen too often, or a cable gets swapped and now the right throttle's controlling the left engine or something like that. Okay. So different things like that use that tactile feel. Switches up top, you have switches that are guarded, are more, like in this case, they're guarded in the flight position. So if you bump that switch, one, it's not going to allow you to switch it, but also you're going to have to be like, okay, I had to flip the guard down and flip the switch. That should make you think that like there's 2 steps now. Maybe there's a reason it takes 2 steps. Or some of your switches where you have to pull out on them to move them, same thing. You got to pull and then switch it. You can't just switch it, right? That's because you don't want to bump them into the off position or bump them into the on position. Okay. Fire handles are almost always these T shape. Some aircraft use a button, but the T shape is pretty common for a fire handle. Okay, so that's the tactile element of things. Okay, and then more of that standardization. Control loading and feedback we'll talk about in flight controls, but that's so we can feel the aircraft. Okay. And then the whole flight deck is designed around what's called the dark flight deck concept. And this is something to keep in mind as someone who's maintaining the aircraft. This is one of those, like, it doesn't seem logical at first until you learn about it. Okay. In your world, what happens if something has a light on it? What happens when you flip the switch on? The light does what? The light shuts off? On. I turned my laptop on. Here's the little power button. The little power light comes on, right? I turned on my microphone. The little light comes on. I flip on the switch when I walk into a room. The light comes on. On an airplane, when something is on or in the normal flight condition, the indicator lights shut off. Okay, it's opposite of what you're used to with the devices around you. Okay, and the reason for that is during a normal cruise flight, normal cruise flight, we want to minimize distractions. If you think about the 727 cockpit when you're sitting in there. When we first turn power on, you've got lights on everywhere, right? What if one light turns on or one light shuts off? Will you even notice it? Probably not. If that whole cockpit's dark and all of a sudden a light comes on when something stops working, will you notice it? A lot easier to notice. That's the idea behind it. Okay, if you minimize all the distractions, it's kind of like the boy who cried wolf. You only make an indication when something goes wrong. You don't make an indication when everything's good to go. Okay, so during normal cruise flight, minimize distractions by having lights off, messages are cleared off your screens, that kind of thing. When something goes wrong, it'll get your attention. I've got kind of a neat video on the Vision flight deck system, which is a very modern version of an ICAS system. So in that short video, the 3 items: dark cockpit, right? Annunciators, another term for like warning lights, come on when there's a problem. Switches, and I mentioned this to some of the groups in the 727. Which way do the switches go? How do we turn a switch on an overhead panel? Push it forward. So don't think about it as up and down. If you do think about it as up and down, you're going the wrong direction. You're pushing it forward to turn something on. You're pulling it back to shut down. Think about how the throttles work. You push forward to make the airplane go. You pull back to make the airplane stop. So they do the same thing with switches. The third item was they talked about rotary switches, and the normal position is straight up and down. And most things are auto, things like contactors and valves and whatnot. But if you need to override them, you can turn them one direction or the other. Okay? And they talk about like it's not unique to the Bombardier Fission. Like pretty much most of your modern cockpits do that. That's just happened. They made a little video about it. The other one is the display screens. Messages only pop up when something is abnormal. So when I say messages popped up, we're talking about an EFIS system. So EFIS is Electronic Flight Information System. Okay, sorry, not EFIS. I'm talking about ICAS for messages pop up. EFIS is Electronic Flight Information System, and this is all of your displays and everything else that essentially replaced traditional analog gauges, and it can also extend to indication and warning. So things you'll see: primary flight displays and secondary flight or multifunction displays, secondary flight displays, and then what's called ICAS or ECAM can be part of EFIS, but it doesn't have to be. Okay? So I'll repeat that. EFIS deals mainly with flight displays, electronic flight information system. Okay, you don't see anything about systems information there. A plane can have EFIS and still use traditional gauges for the systems. Or a plane can have EFIS and have an ICAS or an ECAM system, which is electronic indication. We'll talk about in a second. So flight deck and kind of iterations. Originally, you had all your traditional gauges. Then you had the first instruments to go to electronic were flight, and that's when EFIS started. And then flight and engine instruments, as well as systems information with messages, was developed, and that's where ICAS and ECAM became part of EFIS. So here is your earliest version. This is all traditional gauges. Okay, so no EFIS right here. Okay, this plane has EFIS. Here's your electronic flight displays, but it still has analog engine displays, and if you look at the overhead panel, it has analog system displays, analog system instruments. Okay, this is an EFIS cockpit, but it does not have ICAS or ECAM in it. Okay, it doesn't have systems and engine information displayed digitally. And then here you have a cockpit that is EFIS. It has electronic flight displays in front of the pilot, co-pilot, or pilot, captain, first officer. And now we've got digital displays in the middle that are going to have our engine and system information on them. Here's another version of that powered up. You can see flight information on the left, flight and navigation on the left and on the right. And then in the middle, here's your engine displays and various systems information that can be pulled up there. Now you can see these still have a couple analog instruments in the middle. Who knows what those are? Any idea what those are for? Those are backup. Those are emergency backup. Okay. Even here, you still got some analog gauges. All that information is duplicated on the electronic displays. And the primary one used during flight is the electronic displays. Those physical instruments are used as backup. Okay. The electronics are pretty robust, but even here, 787 still has, now it's got a digital backup display in the middle. It's called an integrated standby instrument, where it has a horizon, speed, altitude, and direction. But this one instrument, not only is it like this, but it's got a battery attached to it. So it can run all by itself, even with a full electrical system failure. So then we get into ICAS, engine indicating and crew alerting system. So this is where we take engine instruments and indication along with written messages that pop up. And then we can also get system and aircraft information using what are called synoptic pages or synoptic screens. We can change what the display shows us in order to see details about various systems. This is what you've been playing with in the simulator, that 747 simulator, where you can pull up the various pages. These, however, are not your flight instruments. Again, they're not going to be on the screens directly in front of the crew. They're going to be between the two crew members. And used by, you'll see these on Boeing, Embraer, Canadair/Mitsubishi, and many corporate jets. Okay, they'll call it an ICAS system. You'll hear the term ECAM as well. And that stands for Electronic Centralized Aircraft Monitor. And I've told this story to a few of you. It's basically the same thing as ICAS, but do not say that to an Airbus engineer who worked on the ECAS system, or their ECAM system. Because I asked one time that I met what the difference was, and he went to this long-winded conversation, and at the end I said, so it's basically an ICAS system. And I think I insulted him. Actually, I know. No. And he went through the differences again, and I still didn't know what was different about it, other than the name. So electronic centralized aircraft monitor, ECAM, engine indicating crew alerting system is ICAS. Pretty much the same thing. It just depends on whether you're looking at a Boeing product or an Airbus product. So what do these look like? Here's a close-up of an ICAS system. You can see, so looking at engine indicating. Here's engine indicating. EPR, N1, N2, EGT. This is N3, so it's got a a Rolls-Royce Trent engine, fuel flow, oil pressure, oil temp, oil quantity, vibe. You can see all that stuff. Boom, boom, boom. Nice and compact right there. You've got messages over here for your different systems, so they can be color-coded. Pressurization information down here, fuel information. Down here it shows the synoptic page with the electrical page here, but you can change this to show any number of systems on the aircraft and get details about them. Okay. Here's another aircraft. This is a 4-engine aircraft with an ICAS system. I don't remember what this is out of, honestly, but another ICAS system. Here the messages are down below on the primary display, some systems information on the secondary display. So anything you work on today is going to probably have ICAS or ECAM in it. Just yeah. I think this is can't remember what it is. Like I said, it's got Rolls-Royce Trents on it. It's got a 3-spool engine, but other than that, I can't remember. Okay. So I'm just going to finish this up. We only have a couple more slides, so it makes more sense just to finish this and come back from our break. So with any of these, you have discrete wiring versus bus architecture. So older aircraft use discrete wires to carry information. So essentially, you can think of like a sensor to a wire to a gauge or an indicator. Okay. Newer aircraft still have that, but they also implement things called bus systems. They have bus architecture. So what I mean by that is if we had a sensor over here, so this is your older system, so here's our sensor. And over here we have a gauge. Okay. Between them, you've got a wire, right? And if you have something else, say you have like a computer or something that also needs that information, now you often are either going to have a second sensor or a second wire, or this gauge and this are going to be tied together, something like that. Okay. If we look at bus architecture, what that means is that we have a common spot for our information. And so rather than discrete wiring, I should have kept my items here. If we have our sensor over here, and I'm going to use, does green show up better? No. Oh boy. Because blue it is. Here's our gauge, or maybe here's our display screen, like our ICAS display. Instead of hooking them directly, we're going to hook into something called a bus. Okay. So the sensor goes to the bus. Various items are connected to the bus, right? And so we can have a bunch of sensors connected to the bus. So the information from them ends up on this bus, and various items that need that information can pull it off of the bus. So that's what the term bus architecture refers to. So say, for instance, you have a pitot probe that gives you airspeed indication, right? You need that to show airspeed on your flight display, right? But you also may need that to operate the Mach trim. Mach trim automatically trims the stabilizer based on different airspeeds. So the pilots don't have to sit there and retrim the stable. When you speed up or slow down, you have to change your pitch trim because the airplane's going to want to nose down at slower speeds and nose up at higher speeds. So Mach trim automatically does that. So you can take that airspeed information, you're going to feed your pilot's speed display, you're going to feed, the Mach trim computer will pull it off of the bus. Maybe on the planes I worked on, if you had to run the APU in flight, the APU door had to open and close more or less so it wasn't ramming too much air into the intake of the APU, right? So you have these different things that can do that. Or altitude, right? Information will be on the bus. Flap position will be on the bus because, depending on where the flaps are, different warnings would have to be indicated, right? If your flaps are down, you start going too fast. You don't want to rip the flaps off the airplane, right? So information can get put onto the bus, and then whatever systems need it are able to pull it off. And there's various buses out there. The original, kind of the earliest one, most common still though, is ARINC 429. The standard was developed in 1977. Originally 12.5 kilobits per second. Now it's up to 100 kilobits per second. ARINC 629 came out later. That's 100 megabits per second. There's other buses. There's a whole bunch of different bus architectures out there. But essentially, have multiple users of the information, computers, other systems and instruments and displays that can all pull information off of there. What's that? Yeah, there's fiber-based buses now. Like there's fiber-based communication systems in the aircraft too. So instead of wires, fiber optic. So if you look at instrumentation versus ICAS, ECAM, most of your discrete instruments were more of a direct wiring where you had a raw view of the data, right? So the flight crew had to monitor it, that flight engineer, whoever. So think about the flight engineer panel. With ICAS and ECAM, it's pulling information off of buses. Again, there is still some stuff that's discretely wired, but a lot less of it. But in this case, now you get often an interpreted view. So there's a computer monitoring it, and it can provide things like messages, or it can show a schematic of a system and kind of turn things green or yellow or red, right? It can compare some different things and give you, it can interpret the results rather than just giving you raw data that you have to say, is that normal? Is it not normal? If it gives you a line that's green, it's probably normal. If it gives you a line that's yellow, it's kind of a, got to kind of deal with that. If that gives you a line that's red, or say your engine turns red because of a fire, that's a, oh crap, I really need to deal with this right now situation. So it interprets that to help you decide how best to deal with a situation or resolve it. And it's dynamic. It can actually change based on like the setup of the aircraft or what phase of flight it's in. Right? Flaps down for landing is normal. Flaps down at cruise speed, not normal. Flaps down at takeoff, little bit normal. Way down like they would be for landing, absolutely not normal. Too much drag. Right, so the plane can change how it reacts to different configurations based on what phase of operation it's in. So there you go. That's what it looks like. Again, discrete, raw data over here, interpreted data pulled off a bus over here on the right. And when I talk about the pages, so that's the main page, but here's an example of synoptic pages, where you'll have a primary display that's always going to show engine, messages, and some basic info, and then typically your secondary display, you've got a status which shows like flight control positions and some doors here. You've got an actual dedicated flight control page, a hydraulic page, a fuel page, electrical, environmental control, anti-ice, and then this one even has a maintenance page. You can go into a maintenance page for troubleshooting and for fault logging and that kind of thing. That's really handy. Pilots had something pop up in flight, but it came up and then it went away. Plane lands on the ground, you're like, yeah, I can't duplicate it. I have no idea what to, But now with maintenance pages, often they log those faults. You can go back and look at what came up during the flight. Yeah, so see what was recorded in the computer. So that's really handy when you have intermittent type faults or faults that only occur when the plane's flying. We've had those before. Plane always works fine on the ground. Then they go up and fly, and all of a sudden you start getting, a flap. They can't put the flaps down. They work great on the ground. They don't work in the air. Why can't we put the flaps down to land? Why do our planes keep having to land without flaps down? We go and look at the fault history. It's showing an overload on the flap drive motor. That tells me something's jamming the flaps, physically preventing them from going down and overloading the electric motor. What could be doing that? Anyone have any ideas? Bird? But then it gets on the ground and they operate them fine. They work fine on the ground. Linkage from the aileron. They're pretty independent of each other. So there's an electric motor that's used to drive the flaps down. The electric motor goes through some actuators, drives the flaps. Motor keeps showing an overload in flight, but it works fine on the ground. Idiot. Nope. Moisture was getting into the flap actuators and freezing at altitude. So the gearbox and the actuators would be frozen solid at altitude. When the plane came down, landed, everything warmed up. They worked just great. Plane went out and flew. It's up at altitude for 2 hours, negative 30 degrees. Flaps freeze solid, flap actuators freeze. You can't get the flaps to go down again. Welcome to 2 years of removing flap actuators, sticking them in a negative 60-degree freezer for 2 hours, and then putting a torque wrench on them to see if we could get them to twist. And sending most of them out for overhaul. They're on design iteration like 40 on those to prevent that. So, having those fault logs, if we didn't know why it kept causing that to fail, it would have made it a lot harder to troubleshoot. It still was a pain to troubleshoot. It still took a lot of people a lot of time. I mean, every operator of that aircraft type was dealing with this. And it took a lot of kind of figuring out to finally figure out what it was. It's really nice having that freezer. You come in with a warm pop, you put it in there 15 minutes later, you get a freezing cold drink. Just don't forget it or it'll explode really quick. But yeah, so that gives us all our information that, before, and this is all interpreted, right? The computer can turn lines green. Yep, that's normal. You got a white line here. It shows it can get power, the essential bus can get power from bus 1, but normally it gets power from bus 2, it's green, okay? So, it interprets that view rather than having to figure out, is the essential bus getting power where it normally would? If it's set to bus 2, is that normal? Is it not normal? Well, we know it's normal on here because it's green.